Hydraulic structures are man-made structures placed within a waterway to develop control. In rivers, hydraulic structures can be used to divert flow into a canal for irrigation, measure flow rates, and control the quantity of water. For example, a dam can be used to reduce flows downstream. We will discuss the following structures in this lecture: weirs, gates, and orifices. All calculations of these structures are based on the energy equation. The first structure is a sharp-crested weir. As mentioned previously, it is based on the energy equation. These lessons are not going to cover how to derive the equations, but just provide them. The following image shows a schematic of a sharp-crested weir. As flow goes over the weir, the depth goes through critical depth at the weir. Therefore, the flow rate can be determined as follows. Q, the discharge, is equal to 2/3 times CD, the coefficient of discharge, times the square root of 2G, where G is gravity, times L, the length of the weir, which is the perpendicular to the flow, so the length of the weir through the paper or through the board, times H, the depth of flow upstream of the weir, raised to a power x. Now the value of x depends on the type of weir we will be discussing. The first weir is a rectangular weir, where the coefficient of discharge is a function of the height of the weir and the depth of flow upstream above the weir. X, the coefficient x, is 1.5. For a tripletti weir, sometimes referred to as a trapezoidal weir, the side slopes are always 1 horizontal and 4 vertical. So this is pretty steep, almost rectangular. However, the coefficient of discharge is always assumed to be 0.63, and the value of x again is 1.5. For a V-notch weir, theta becomes a very important aspect. When theta is 90 degrees, the angle of the V, then the coefficient of discharge is 0.8, and the value of x is 5/2. For a 60-degree V-notch, CD is equal to 0.46, and x is equal to 5-2. Next, we will discuss the broad-crested weir, which has a long parallel length with respect to the flow. The following schematic provides a detailed overview of the flow over the weir. As previously mentioned, in a sharp-crested weir, it is also true in a broad-crested weir that as the flow goes over the weir, the flow depth is critical, as you can see in the schematic DC. The discharge over a broad-crested weir is equal to the weir coefficient, CW, times the length of the weir. This is into the board, not the width of the broad-crested weir. H, the depth of flow upstream of the broad-crested weir raised to the 1.5 power. So how do we determine the weir coefficient? The weir coefficient for a broad-crested weir is based on the following table, where in the first column you see the height H of the weir, or of the depth of flow upstream of the weir. And on the first row, it's the breadth of the weir, or the B, how long it is. And so it ranges from anywhere from 0.5 feet to 15 feet. So you can get an estimation. Next, we will discuss gates. Gates are structure used to control flow and to create a known water surface. Calculating the depth of flow is based on the energy equation, where the energy upstream of the gate and downstream of the gate are equal. These schematics show both a vertical sluice gate or a radial gate. In both cases, you can see that the energy equation upstream is equal to the energy equation downstream. Finally, an orifice will be discussed. An orifice is a structure that controls water. The following schematic shows an example of flow exiting a reservoir, where the flow out of the reservoir will act like an orifice. The flow at the top of the reservoir is open to the atmosphere. In addition, the flow leaving the reservoir is also open to the atmosphere. Therefore, pressure does not come into place, and we continue to use the energy equation. And the flow rate is equal to the coefficient of discharge of an orifice, which is 0.6, times the area of the orifice, times the square root of 2 times g, and the change in depth, h2, the depth at the top of the reservoir, and h1, the depth to the center of the orifice. This is very important to remember, to the center of the orifice. The following schematic provides you an even more detailed view of how a system might work, where you might have flow going in a reservoir and then going through multiple pipes to exit out. Now during class we will do some practice to make sure to solidify these concepts, but please watch this video again to be clear about how the equations work and to understand how to apply them.